The basic idea of backpropagation is to guess what the hidden units should look like based on what the input looks like and what the output should look like. So the way it works is it's an online algorithm. It receives data points one at a time. So we get our observation x with d different attributes, x1 through xd. We use those observations with our current set of weights. Remember, each one of the edges has a weight on it. So we use those weights to compute the values of each of the hidden units. And we can do it because the input is fixed, the weights are fixed, so we can compute all the hidden units. Right? And at each case, all we're doing is we're just running the sigmoid. So we're looking at the nodes f that influence g. We're multiplying them by the weights that connect f and g, adding them all up, adding a bias term, and putting it through a sigmoid. So very, very straightforward. You can do it layer by layer until you get all the way to the end of the network. And at the end, you're going to get y, and y is your prediction for the class. It's what you're trying to predict. So at the end, we're going to get our prediction y. We also know what is the true label for this example. So the y star, that's the target class or the target value of the output. So we can compute the error, how far we are from the output. And the cleverness of the backpropagation algorithm is then we're going to take these errors and starting with the y, we're going to push them back. So we have an error on the y. This tells us whether the output of the whole network should be higher or lower. Right? And we're going to use that to figure out if h1 should be higher or lower, and h2 and h3. And once we figure those out, we're going to use these values to figure out if g1 should be higher or lower. So what we're doing is you're creating sort of synthetic training examples for all the hidden units in your network. Now, the way it's going to work is the way these errors are propagated is according to this equation. So what you're doing is you want to figure out, so we're computing the derivative of the error with respect to some unit gj in the network. Think about it. The derivative of the error, the interpretation is that tells us whether gj should be higher or lower. Right? That's our interpretation of the derivative. So how do we know if gj should be higher or lower? Well, we assume that we have already figured out if, for all the h units, if they should be higher or lower based on the y. Right? Now, this unit gj, it affects all the h units. Right? So when we change gj, it's going to change all of their values. So we want to know, should gj be higher or lower? So what we do is we look at, did we want each of the h units to be higher or lower? Right? And then this part of the equation, that's an encoding of, as we change gj, how will hi change? And it's really pretty simple, right? So you have the weight connecting I and j. So as I change gj, it's going to get multiplied by this weight vij, and that's how it will affect the unit hi. The other part here is the derivative of the sigmoid. Right? It happens to be because all of the nodes are sigmoids, and by chain rule that thing pops up all over the place. It may look intimidating. It's really just a function that looks like that. So it's a scaling function that says that if h was around 0, then whatever changes you make to g will affect h a lot. So you have a high value around 0. And if h was already very close to 1 or very close to 0, any changes are not going to affect it. So the weights are close to 0. So if you added up over all the nodes h in the hidden layer, you get an estimate of whether g should be higher or lower. Great. So now I know if I want g to be higher or lower. The next step is to update the weights connecting g to the nodes that feed into g. Now I know I figured out if I want g to be higher or lower. Now I want to figure out if that edge connecting fk to gj, if that should be higher or lower. And that is actually really, really simple. So you don't need to sum up anything. You just need to take the value of fk, right? What value of k had previously, and the current weight, right? So fk times ujk, that's just one component of the sum that feeds into gj. So I just need to differentiate. And the derivative is really, really simple. So the derivative of the error with respect to this, to the value of the weight ujk is just the derivative with respect to g, whether I want g to be higher or lower, times how g will change if I make u higher or lower. So that allows you to compute the derivative on the strength of connection. And then once you have that derivative, remember that derivative just tells you whether the strength should be higher or lower. So you update it, and you update the weight in the same way that we did for logistic regression. You take the weight and you subtract a certain amount of the derivative that will minimize